Episode 10: The Great Dying. Permian Extinction wipes out 90% of species. Part 1: The Carboniferous World, Forests, Fire, and Oxygen. Introduction: A planet of forests.
By 359 million years ago, the Carboniferous period opened on a planet draped in green. From Devonian survivors arose vast lowland forests across the equatorial supercontinent Euramerica. Tree ferns, lycopsids, horsetails, and seed ferns rooted in deep, waterlogged soils, their crowns knitted into canopies stretching for hundreds of kilometers. The air grew dense with moisture and, increasingly, with oxygen. For the first time, the continents functioned as a planetary lung. Forests drew down carbon dioxide, buried organic matter, and exhaled oxygen into the sky. During the Carboniferous period, about 359 to 299 million years ago, Earth went through two main chapters called the Mississippian and Pennsylvanian. At this time, carbon dioxide in the air dropped to very low levels, while oxygen rose to around 1/3 of the atmosphere, the highest it has ever been. Huge amounts of plants were buried in swampy wetlands, locking away carbon and causing this change. As a result, the air became thicker, which slightly affected how animals breathed, how fires burned, and even how the climate worked.
The coal forests.
Equatorial regions were dominated by swamp forests, labyrinths of standing water, floating peat, and towering lycopsid trees such as lepidodendron and sigillaria, some over 40 meters tall. Their trunks bore diamond-patterned scars. Their roots formed dense underground networks in waterlogged soils. Beneath the canopy, shade-tolerant plants thrived amid pools, fallen trunks, and decaying litter. Death in these wetlands did not mean rapid decay. Fallen trees and leaves sank into anoxic bogs where bacteria worked slowly. As sediments accumulated, thick peat layers formed. Over millions of years, burial, heat, and pressure compressed these peats into coal, vast, black archives of a world ruled by plants. In the Pennsylvanian period, some coal layers grew to be as much as 30 meters thick, far larger than anything we see forming today. These layers often appear in repeating patterns with sandstone, showing that sea levels were rising and falling as the planet shifted between ice ages and warmer times, guided by changes in Earth's orbit. The chemistry of nearby limestone rocks reveals that huge amounts of carbon were locked away underground, which helped oxygen in the atmosphere steadily climb higher.
Giants of air and swamp.
Oxygen-rich air transformed animal possibilities. Arthropods, whose respiration depends on diffusion through tracheae, achieved sizes impossible today. The skies held dragonflies like Meganeura with wingspans approaching 70 centimeters. The forest floor hosted Arthropleura, millipede-like giants over 2 meters long. Amphibians, liberated by abundant wetlands, diversified into a wide range of body plans, from slender insect eaters to bulky semi-aquatic predators. Among them appeared a new kind of vertebrate, small, lizard-like reptiles that laid amniotic eggs protected from desiccation. These early amniotes could reproduce away from open water, creeping into drier microhabitats at forest edges and uplands. When oxygen made up about 35% of the air, insects could grow up to 10 times larger than the biggest ones alive today, which matches the size of the largest insect fossils we found. Around the same time, early reptiles like Hylonomus, about 312 million years ago, had strong legs for walking on land and eggs with tough, leathery shells. These features marked a key step in evolution that eventually gave rise to reptiles, birds, and mammals.
The Fire Age.
High oxygen had a cost. Vegetation ignited easily. Lightning strikes over humid forests sparked frequent wildfires. Flames raced through canopy and undergrowth, leaving behind charcoal-rich ash layers. Fire became a central ecological process, clearing old growth, recycling nutrients, and shaping plant evolution. Species with thick bark, rapid regrowth, or spore releases timed to follow fires prospered. In the Carboniferous period, many coal deposits contain 5 to 15% fossil charcoal, evidence of ancient wildfires. Experiments show that when oxygen in the air rises above about 25%, fires can keep burning on their own. The large amount of charcoal in these rocks tells us that oxygen was very high back then, and that frequent fires helped stop oxygen from climbing even higher by burning plant material and sending carbon dioxide back into the atmosphere.
Climate cycles and ice.
While the tropics teemed with life, the southern supercontinent Gondwana lay under extensive ice sheets. The Carboniferous climate oscillated between glacial and interglacial states, driven by orbital cycles and continental geometry. During glacial maxima, sea levels fell and coastal swamps shrank. During interglacials, meltwater flooded lowlands and peatlands expanded. The rock record preserves these pulses as alternating marine and terrestrial layers, the heartbeat of a forested, glaciated world. Glacial deposits from South Africa, South America, and Australia date between 335 and 295 Ma, confirming a prolonged Gondwanan ice age. Oxygen isotope shifts of up to 2 per thousand correspond to global temperature swings of several degrees, in tune with 100,000-year eccentricity cycles. Coal-forming wetlands waxed and waned with these sea level changes, coupling ice volume to oxygen and carbon cycles.
The end of the coal forests.
In the late Carboniferous, tectonic drift drew continents together. As Pangaea assembled, mountain building reshaped atmospheric circulation. Interior basins dried, monsoons weakened, the equatorial wet belt narrowed and fragmented. Coal forests that had once formed continuous belts across Euramerica and beyond retreated into refuges along coasts and river plains. Drought-tolerant seed ferns and primitive conifers replaced swamp flora on uplands. Around 305 million years ago, Earth's rainforests suddenly broke down. We can see this because coal, which forms from dense plant life, stopped building up, and the variety of plant spores dropped sharply. At the same time, chemical signals in the oceans show that less plant material was being buried, which marked a turning point in the amount of oxygen in the air. Rising mountain ranges like the Appalachians and Veriskans changed wind and rainfall patterns, slowly breaking apart the wet, lush climate system that had kept oxygen levels so high during the Carboniferous period.
Conclusion: the peak of breath.
The Carboniferous was Earth's great experiment in oxygen. Its forests buried staggering amounts of carbon and pushed oxygen to levels never again reached, allowing giant arthropods, extensive fires, and dense swamp ecosystems. Yet this abundance depended on a delicate interplay of climate, sea level, and tectonics. As continents fused and climates dried, the wetland engine faltered. The age of forests drew down its own curtain, and a new, harsher world emerged, the stage on which the Permian drama would unfold.
Part 2: The Permian Transformation. Continents unite, climates dry. Introduction: A changing planet.
As the Carboniferous ended, Earth's geography and climate reorganized. Over tens of millions of years, collisions between continents created the supercontinent Pangaea, a single landmass stretching from pole to pole and spanning much of the globe. Its vast interior lay far from the moderating influence of oceans, fostering seasonal extremes and immense deserts. The humid, coal-forming forests shrank to coastal fringes and highlands. Seed plants with drought-resistant traits, conifers, cycads, ginkgos, and glossopterids, spread over upland plains. Meanwhile, atmospheric oxygen declined and carbon dioxide rose. The Permian world was biologically sophisticated but environmentally unstable. The Permian, 299 to 252 million years, saw carbon dioxide rebound from under 1,000 ppm to around 2,000 ppm, while oxygen fell from roughly 30% to near 15%. Charcoal content in coals plummets during this interval, indicating reduced fire frequency and lower oxygen. Global temperatures climbed to averages near 28 degrees Celsius, with polar regions largely ice-free. The consolidation of continents also altered ocean circulation, predisposing basins to stagnation and anoxia.
Pangaea, the supercontinent.
Pangaea's assembly was one of the great tectonic revolutions. The closure of multiple oceans raised a continuous chain of mountains from North America through Europe into Asia. These ranges diverted wind belts and monsoons, generating hyperarid interiors. Seasonal temperature swings of 40 degrees Celsius or more likely characterized inland plateaus, while coastal margins experienced intense, sometimes erratic rainfall. Orogenic belts such as the Appalachians, Variscans, and Urals record collision between continental blocks between 320 and 270 million years ago. Climate simulations show that such a configuration produces strong monsoonal cells around Pangaea's margins and vast subtropical deserts in its center. Dust from these drylands, preserved as red beds and loess, testifies to frequent storms and long-distance sediment transport. The closure of seaways also restricted deep water formation. Without vigorous polar sinking, the oceans circulated more slowly. Deep basins became prone to oxygen depletion, and black shales with pyrite and organic matter accumulated even before the final crisis. The marine world was becoming stratified, thin oxygenated surface layers floating above expanding oxygen-poor depths.
The new flora and fauna.
The shift to a drier climate drove a turnover in life. The old coal forest flora of lycopsids and tree ferns declined. In their place, seed plants flourished. In the south, glossopterid forests spread across Gondwana. In the north, conifers and ginkgos dominated uplands. Their seeds and tough leaves allowed survival through seasonal drought and cold. On land, reptiles seized the initiative. Amphibians, tied to water for reproduction and vulnerable to desiccation, retreated to moist refuges. Synapsids, the mammal-like reptiles, diversified into herbivores with deep bodies and broad teeth, and predators with large skulls and sailbacks for thermoregulation. Later synapsids, the therapsids, evolved differentiated teeth, more upright limbs, and higher metabolic rates, foreshadowing the mammalian condition. Glossopterid fossils, with distinctive tongue-shaped leaves, occur across India, Australia, South Africa, and Antarctica, providing key evidence for Gondwana's former unity. Synapsids such as Dimetrodon and Edaphosaurus in the early Permian, and therapsids like Mosechops and Gorgonops later, show a trend toward more active, endotherm-like physiology, an adaptation to the wide ranges and harsh climates of Pangaea.
The desert kingdoms.
By mid-Permian time, Pangaea's interior supported vast dune fields, salt flats, and ephemeral rivers. Wind-blown sands piled into dunes hundreds of meters high. Seasonal floods carved temporary channels and left behind mud-cracked flats. Insects evolved tougher exoskeletons. Beetles and cockroach-like forms were well suited to aridity. Reptiles with scaly skin and efficient kidneys thrived where amphibians could not. The Coconino sandstone in North America and equivalent redbed formations in Europe preserve large cross-bedded dunes and trackways of reptiles moving confidently across dry sand. Interbedded evaporites, halite, gypsum, and hydrite indicate cycles of lake filling and complete desiccation. These deposits document a supercontinent whose heartland was as dry as any desert in later Earth history.
The oceans of the Permian.
Around Pangaea spread the enormous Panthalassic Ocean and subsidiary basins like the Paleotissese. With little polar ice and restricted circulation, these waters warmed and stratified. Life flourished in some shallow shelves, where reefs of sponges, algae, and early corals developed, but deeper zones increasingly slipped into anoxia. Permian marine sections in China, Russia, and North America contain black shales with fine pyrite and enriched trace metals, diagnostic of low oxygen conditions. The turnover from brachiopod-dominated faunas to more resilient bivalves and ammonoids reflects adaptation to these stressed environments. Carbon isotope swings of several per mil suggest a carbon cycle already prone to disruption before the final catastrophe.
Decline of the oxygen world.
As coal swamps vanished and previously buried organic matter was uplifted and oxidized, the oxygen surplus bled away. Fire frequency dropped, charcoal became rare, giant insects disappeared. Animals adapted to thinner, less oxygen-rich air, respiratory surfaces expanded, and thoracic cavities enlarged. Inertinite content in late Permian coals falls below 3%, consistent with oxygen near or below 15%. Nitrogen isotope data indicate reduced oxidative processes in soils and waters. Insects shrink in maximum size, and vertebrate fossils show trends toward more efficient breathing structures, a physiological response to an atmosphere that no longer offered superabundant oxygen.
Conclusion: the fragile equilibrium.
By the late Permian, Earth seemed to have reached a new equilibrium, a unified continent, sophisticated plant and animal communities, and a climate generally warm but capable of regional extremes. Yet under this apparent stability lay vulnerabilities: stagnant oceans, declining oxygen, and a carbon cycle easily perturbed. The biosphere that had once cooled the planet and filled it with breath was losing its tight control over chemistry. It would take only one additional shock to tip this system into chaos.
Part 3: The Catastrophe, the End Permian Mass Extinction. Introduction: The breath of the Earth fails.
Around 252 million years ago, the long balance of the Paleozoic biosphere broke. For over 100 million years, forests, reefs, and deserts had exchanged gases with the sky in a relatively stable rhythm. Then, in a geologic instant, that rhythm collapsed. A flood of volcanic fire in Siberia injected unprecedented amounts of carbon and toxins into the atmosphere. Oceans warmed, stagnated, and turned poisonous. Land surfaces were scoured by acid rain and heat. In this brief interval, about 90% of marine species and 70% of terrestrial vertebrate genera vanished. The Paleozoic ended in a single, devastating Great Dying. High-precision UPB dating of boundary layers, especially at Meishan in China, shows that the main extinction pulse lasted less than 60,000 years. Fossil counts indicate an order-of-magnitude drop in marine diversity. This was not a slow decline but a sharp cliff in the history of life.
The Siberian Traps.
The immediate trigger was the eruption of the Siberian Traps, a large igneous province covering several million square kilometers. Over roughly a million years, great fissure eruptions poured lava across northern Pangaea. Each pulse released carbon dioxide, sulfur gases, and halogens. Lava intruding into coal and carbonate beds baked additional greenhouse gases out of the crust. Estimates of total lava volume exceed 3 to 5 million cubic kilometers. If each erupted batch released carbon dioxide at rates comparable to modern flood basalts, cumulative emissions easily surpassed 10,000 gigatons of carbon. Contact metamorphism of underlying coals and evaporites may have added thousands of gigatons more, including methane, a far more potent greenhouse gas. Mercury spikes and sulfur isotope anomalies in boundary sediments record repeated episodes of intense degassing, acid rain, and stratospheric damage.
Runaway greenhouse.
The climatic response was swift. Atmospheric carbon dioxide soared to many times pre-eruption levels. Global temperatures climbed by 8 to 10 degrees Celsius. Tropical seas warmed to near lethal temperatures. Land surfaces in equatorial Pangaea approached 35 to 40 degrees Celsius, stressing plant and animal physiology. Rain became acidic, stripping soils and releasing metals and nutrients into rivers and coastal waters. Ocean acidification dissolved shells and undermined carbonate-producing organisms. At this boundary in Earth's history, evidence from tiny fossil teeth shows a sudden jump in temperature. At the same time, chemical clues from ancient rocks reveal that the oceans became more acidic, with pH levels dropping close to 7. This made the water nearly unable to hold the minerals needed for shells. For many creatures that built shells, the environment crossed a critical line. They could no longer grow or survive.
The poison seas.
As the climate warmed and more nutrients flowed into the oceans, the water became layered. The surface stayed warm and held oxygen for a while, but the deeper layers stopped mixing and lost oxygen. Dead plants and animals sinking down made this worse, and bacteria that produced toxic gases spread. Eventually, waters filled with hydrogen sulfide, poisonous to most life, rose up into shallow seas and even into the sunlit surface zone. Black shales at the Permian-Triassic boundary show iron speciation signatures and tiny pyrite framboids typical of Euxinia. Biomarkers such as isorenirotane, produced by green sulfur bacteria, demonstrate that sulfide-rich waters extended into the photic zone. Models suggest that hydrogen sulfide outgassing could have damaged the ozone layer, letting UV radiation further stress life on land and in shallow seas. Reefs collapsed first, followed by brachiopods, corals, crinoids, trilobites, and many plankton. Food webs unraveled from top and bottom simultaneously. Predators lost prey. Primary producers lost habitable niches. In some regions, only a few opportunistic species clung on in the aftermath.
Collapse on land.
On land, the same forces wreak havoc. Acid rain and heat killed forests, leaving bare soils vulnerable to erosion. Dust storms scoured plains. Rivers carried silt, metals, and nutrients into already stressed coasts. Glossopterid and conifer forests disappeared. Fern-dominated floras briefly expanded into the gaps, a disaster flora signal seen worldwide. Herbivorous synapsids lost their plant food. Carnivores starved as prey dwindled. Only small, generalist, often burrowing animals had the resilience to survive. In South Africa's Karoo Basin, vertebrate assemblages shift from diverse communities of large Decinodonts and Gorgonoptions to impoverished faunas dominated by the small burrowing Lystrosaurus. Bone histology shows growth interruptions and signs of stress. Pollen and spore records reveal sharp turnovers, including global fern spikes indicative of rapid colonization of devastated landscapes by hardy plants.
The final pulse.
In the global rock record, the peak of the catastrophe corresponds to a thin, dark layer rich in soot, ash, and chemical anomalies. Carbon isotope values plunge by 6 to 8 per thousand, reflecting the oxidation of vast stores of organic and methane carbon. Extinction peaks coincide with maximum warming, most severe anoxia, and strongest geochemical shifts. At Maishan in China, scientists study a thin rock layer less than a meter thick that captures signs of a global disaster. It shows unusually high mercury from massive volcanic eruptions, chemical shifts that reveal a collapse in plant and animal life, and strange patterns in elements like selenium and sulfur that suggest Earth's normal cycles broke down almost completely. After this point in time, many types of ancient life from the Paleozoic era disappeared forever.
Conclusion: the long night.
The end Permian extinction was more than a spike in volcanic activity. It marked a moment when feedbacks that had kept climate and chemistry within habitable bounds were overwhelmed. Carbon, once cycled by life in stabilizing loops, surged uncontrollably through atmosphere and ocean. Heat, acidification, and anoxia pushed Earth close to biological reset. Yet even here, life did not vanish completely. A few lineages endured through the worst conditions the planet has seen since complex life evolved, setting the stage for a slow and radical recovery.
Part 4: Aftermath and Recovery, the Triassic Dawn. Introduction: a world of ash and silence.
When volcanic fury waned and the climate began to stabilize, the world that remained was unrecognizable. Many landscapes were stripped to bare rock and thin soils. Rivers ran with chemically loaded waters. Seas were murky, acidic, and still oxygen poor. For hundreds of thousands of years, ecosystems were dominated by disaster taxa, hardy, opportunistic organisms that could tolerate extreme conditions. Early Triassic sediments frequently show disaster facies, monotonous sandstones and shales with low diversity, often dominated by a single bivalve or brachiopod genus. Carbon isotope values remain depressed for several 100,000 years, indicating a carbon cycle still far from equilibrium. Trace metal proxies show that deep ocean anoxia persisted for at least 2 million years after the main extinction pulse.
The survival biota.
In the oceans, thin-shelled bivalves, simple ammonoids, and microbial mats colonized seafloors largely devoid of complex communities. On land, a few synapsids, notably Lystrosaurus, and tough ferns and seed ferns spread across devastated terrain. These survivors, not particularly impressive in size or specialization, had the crucial advantage of resilience, fast reproduction, generalist diets, and tolerance of heat and hypoxia. In some earliest Triassic formations, Lystrosaurus fossils make up more than 80 to 90% of vertebrate remains. In marine strata, Chlorea bivalves occur in dense, nearly monospecific beds. Such dominance patterns reveal ecosystems simplified to a few robust forms, with most ecological roles temporarily vacant.
The long recovery.
Recovery from the Great Dying was slow and uneven. For millions of years, climatic and chemical instability persisted, with secondary carbon pulses and smaller extinction events interrupting rebounds. Yet gradually, diversity returned. Marine ecosystems saw the rise of new groups: modern-style corals, scleractinians, neogastropods, and diversified ammonoids. On land, synapsid survivors gave rise to cynodonts and early mammal relatives, while reptiles radiated into new forms. Recovery from the Great Dying was slow and uneven. For millions of years, climatic and chemical instability persisted, with secondary carbon pulses and smaller extinction events interrupting rebounds. Yet gradually, diversity returned. Marine ecosystems saw the rise of new groups: modern-style corals, scleractinians, neogastropods, and diversified ammonoids. On land, synapsid survivors gave rise to cynodonts and early mammal relatives, while reptiles radiated into new forms. By about 247 to 240 million years, carbon isotope curves trend positive and stabilize, indicating renewed organic burial and a rebalanced carbon cycle. New coral reefs appear, and trace metals suggest improved ocean ventilation. Biodiversity studies show that it took roughly 5 to 10 million years for ecosystems to regain moderate complexity, and up to 30 million years to reach pre-extinction global diversity levels.
The new atmosphere and climate.
As vegetation re-established itself, the terrestrial carbon and oxygen cycles rebooted. Weathering of volcanic rocks and uplifted sediments drew down carbon dioxide. Soils thickened. Charcoal returns to the rock record, signaling a rebound in oxygen and the comeback of fire. Climate remained warm, especially at low latitudes, but extremes softened compared with the crisis peak. Monsoonal patterns over Pangaea generated belts of forest, savanna, and desert. Rocks from the Middle Triassic show signs that Earth's air had plenty of oxygen, even more than today. Charcoal remains suggest frequent fires, which need high oxygen to burn. Coral reefs from this time record tropical seas about 30 degrees Celsius and normal ocean chemistry, clear evidence that the oceans had bounced back from earlier acidification and oxygen loss.
The rise of the archosaurs.
On this reconstructed stage, new rulers emerged. Among reptiles, the archosaurs, with upright limbs, efficient lungs, and high aerobic capacity, radiated into predators and herbivores across Pangaea. From them would later evolve crocodiles, pterosaurs, and dinosaurs. Synapsid survivors diversified too, producing cynodonts with more mammal-like jaws, teeth, and perhaps fur. The Triassic became a laboratory for modern ecosystems. Fossil assemblages from Triassic basins in South America, Europe, and China show the rapid spread of archosaurs within 10 to 20 million years of the extinction. Early dinosaurs appear by the late Triassic, while mammaliform synapsids arise from cynodont ancestors. The Great Dying thus cleared ecological space that these new clades would fill, reshaping the trajectory of vertebrate evolution.
A planet reforged.
By the end of the Triassic, the scars of the Great Dying were obscured by new growth. Coral reefs once again ringed tropical coasts, conifer forests cloak highlands, river valleys supported diverse faunas of reptiles and early mammals. The biosphere was not a restored Paleozoic world but a fundamentally new one, built on different players and relationships. The Mesozoic Earth, the world of dinosaurs, early mammals, and modern-style oceans, arose from the ashes of the Permian. Geochemical models suggest that total organic carbon burial during the Triassic exceeded the losses from the extinction, effectively resetting the long-term carbon and oxygen cycles. The supercontinent Pangaea remained in place, but under a climate and biosphere that had learned to operate under different rules.
Conclusion: life's second beginning.
The Great Dying stands as the most severe test life has faced since it began. It shows that the biosphere and planet are coupled in a feedback system that can, under extreme forcing, spin into catastrophe. Yet it also shows that life is tenacious. From a near-sterile world, Evolution rebuilt complexity, inventing new forms and ecologies. Warm-bloodedness, more efficient lungs and circulation, and new reproductive strategies all flourished in the post-crisis world. The Permian extinction thus marks both an end and a beginning, the final chapter of the Paleozoic and the prologue to the age of dinosaurs and mammals. Earth had passed through fire, poison, and near suffocation, and emerged into a new era, carrying forward the lessons of its greatest dying.